Welcome to the June 2024 meeting of the Chicago, Illinois, and beyond Quantum Computing Group. Our speaker today is Harny Wang, who is a senior research scientist and the head of ZX Calculus Research at Quantinuum. He's going to talk to us about the world of processes described by ZX Calculus. Harny, share your screen and tell us all about it.
Okay, thank you. Let me do it. Okay. So hello everybody. Okay, thank you for having me. So today I will talk about the ZS calculus. So I will talk from the background to see to give you a background. So what is behind the idea of ZS calculus? So I will talk about the general process theory, and then I will talk about the theory of ZS calculus. And at the end, I will talk about the applications of the ZS calculus. So first, according to Whitehead, so everything in the world can be seen as a process. For example, so if you like cooking, so you have raw potato, and then you cook it, you roasted it to roast the potato, and this cooking can be seen as a process from raw potato to roasted potato. So that's an example. So everything can be seen, in the world can be seen as a process, but we want a both intuitive and mathematically strict theory for the general processes. That's what we want. So how do we do that? So the idea is, okay, so let's abstract a general process to see what it is. So basically, each process is a change from something. We give a name, so, as A to another thing. We say B, and so we call this process as a name F, and we draw it as a box from A to B. So usually we read from top to bottom. Some people read from bottom to top, but now we just read from top to bottom. And so the general process, we just draw it as a box F. So and it changed from a type A to type B. The A and B could be the same, but in general it's just A and B. And then, okay, that's a denotation of general process. But then how do these processes they interact with each other? So basically there are two ways. So one way is that so two processes, they must either they happened sequentially, that one happen after another. So for example, if we have process G from C to A, and if we have another process from A to B is F. So we can compose them as a single process. Then I show it as on the left. So from C to B, the big box. So this is a composition of the two processes, G and F. So we first do G and then we do F. So I use a little circle as F O G as a sequential composition of these two processes. But of course you can do it arbitrary times. I mean finitely, right? So if you have a process F1 on the Fn, you have n processes, and you can if they can how to say happen one after another, then you can compose them together. Then you can see the whole processes, the whole thing. You can see all these processes which happen sequentially as a whole process, which have changed from A0 to AN. So that's one way you can interact. The processes can interact with each other as they happen sequentially, then you can compose them to see them as a big process. And another way is that, okay, how about if two processes, they happen simultaneously at the same time, then, okay, then the easiest way to represent them is, okay, I just put them side by side. Let's say a process F happened, and at the same time, a process G happened. So I put these two boxes which represent these two processes, right? And then I can see this as another big process, which means, okay, at the same time, there are two things happened. Then so the type, I put them together as I use a lead circle with X inside, with multiplication inside. So it's we read it as tensor. So A tensor C to B tensor D. So that's the whole process if you put them together, if they happen simultaneously. So of course, if there are a few of them finitely, a few of them happen at the same time, let's say G1 to Gn, if they happen at the same time, and I can compose them. So that means I put them together and to see them as big processes. So that means at the same time, a lot of processes happened. Okay, so these are basically two basic ways to compose processes. That means either they happen sequentially or they happen at the same time. So of course, I mean, they can there is that's two ways to see if some so for in general, so processes could happen both some processes happen at the same time, some processes happen sequentially. So how about if we consider these two cases, what would happen? So in general, to make it mathematically compatible, we need to let them to set this sequential composition and the parallel composition need to satisfy what we call interchange rule. So what it is, that means, okay, if I have two processes, so if I have four processes here, like here. So I have two ways to compose them all together as a single process, big process. So how do we do that? So either if we see the first the top two processes G1 and G2 as a single process, that's here G1 tensor G2. So that's a single process. We see them as single process, and then we see the bottom two processes F1 and F2 as a single processes, F1 tensor F2. These big processes, and then because in the middle, the type, they're the same. The B1 tensor B2 and B1 and B2. So I can compose them sequentially. So I compose them sequentially. The two top processes G1 and G2, I compose them first, and F1 and F2 at the bottom, I compose them second, and then I compose the whole two big processes. Or in another way, I can first sequentially compose G1 and F1, and at the same time I can compose G2 and F2, right? Then I get F1 composed with G1, F2 composed with G2, and then I see them respectively as a whole process, and then I compose them in parallel, right, at the same time. So I will get this diagram. So this diagram, but these just two ways, right? These just two ways to compose these four processes. This should, but essentially they are the same, right? That's the same. So this should satisfy that, okay, these are the same processes. That's the same processes, basically.
So I just have a question. Is it intentional then that the two diagrams in the lower half are identical to one another?
Uh-huh.
Okay.
Yeah,
They're not meant to be different. Okay.
Yeah, could be identical, yes. Yeah. So yeah, this code interchangeable. So that's easy to understand, right? Okay, is there any other restriction to or is there any other thing the processor should satisfy? Then that's a problem. So because we said, okay, we put the two simultaneous happen processes in parallel, right? In a plane, right? In a plane. So then because we write down them in a plane, then the problem is, okay, although we said they happen simultaneously, but when we write down them, one has to be on the left and the other has to be on the right, right? So, but if you write, so which one should on the left, which one should on the right? It's kind of artificial, right? So this is a kind of artificial symmetry, right? Not so. What do we do with this artificial asymmetry?
Okay, I found this on the web for measuring
sorry.
synergy. Check it out.
Why is so the problem is we just need to introduce a symmetry process, which is drawn as a swap AB to BA, and then so what kind of property we want these symmetry processes have such that we can solve this artificial asymmetry. So first, this is swap. That means, okay, if you swap them twice, right, they should be the same. It should be identity, should be do nothing. And also, we would like, if we swap the place of two boxes, which happen simultaneously, like FG to GF, right, to GF, they should essentially the same. They should essentially the same. So that means, okay, I just introduce swap. They should essentially the same, but not exact the same. They can't be exact the same because the type, the top is AC. If you just change the place, just change place from FG to GF, then you got the type should be C and A, right? So they're not the same order. So in this case, the type doesn't match. When we say the type match, the order should be the same. Order should be the same. So we use a swap. So when it's F on the right, G on the F on the left, G on the right, then the input input types are A and C. So for G and F, the types are C and A. So we need a swap to let it be to let it change to swap to A and C. And similarly for the output of the F and G. So if we introduce this equation with general processes, and then we solve this problem, the artificial asymmetry problem. So all these are the basic how to say it, the basic ingredients of the process theory. But that's for general process theory, right? But here in this talk we want to care about quantum processes. So how can we depict quantum processes? So the answer is, okay, we can use idea of the calculus, which is the topic of this talk. So this idea was first introduced by Bob Cook and Ross Duncan in 2008. So I will give the more details for this CS calculus. But first, the idea is, okay, so now how do we depict the quantum process, not general process? That means the box. So we use general box for the processes. But now the box should be special, right? So how is the quantum processes depict in this special in a special way as shown in this calculus? The idea is very simple. We just fill in the process boxes with the following two kinds, the green one and the red one, two kinds of spiders, just green and red. So now just green and red. They looks like spiders, so we call them spider. And another types, before we just say, oh, general type, but now the types, okay, we just fix them. The types just numbers, and for the green spider, the numbers can be any can be any natural numbers. But here the for the green spider, for the red spider, so it can be each leg can be the same type. You don't need to let them to be different. So but for the green spider, you can let them to be different. And then I will show later that once you fill in the process boxes with these green or red spiders, and if they satisfy some rules which we call rewriting rules, I will explain what is rewriting rules later. And then they can then we can say that okay, this is exactly a quantum processes. So that's the idea. The use of spiders and some rules. Okay, so but this is very general, very general. So to make it easy, we just consider for quantum process. Let's just consider qubits. Okay, just qubits. Okay, so what is the idea of qubits for the ZX way to fill in the general process box? So basically, we can do it in a Lego way. So you can treat this green spider and the red spider as a Lego. So now because we just focus on qubits, so each leg have the same type is number 2, the types 2. So we ignore the type now for the type and this is the cartoon style diagram. I will show the formal diagram later. So basically you have 2 diagrams, 2 spiders, green and red. They can labeled as with some alpha, that's real numbers. And so how do you then these spiders represent quantum processes? So how do they connect with? How do they interact with each other? So basically, as we said, there are 2 ways. Either you use the sequential composition, or use the parallel composition. So here for these spiders, these 2 compositions are very easy. So the sequential composition just means okay, you just connect the legs of spiders. The parallel composition is also very easy as before. You just put them in parallel. That's the way. And then what is their behavior basically? So informally, so the same color spider. Let's say now it's green spider. They love each other, and when they meet, that means when they connected with just 1 leg is enough. More than 1 leg is fine. And then they were fused with each other. And then if the parameters will sum up, so become alpha plus beta. And the similar for the same for the red spider. If they meet each other with the same color, the red color, and then if they connect it, that means at least 1 leg are shared. Then they just fuse together, and then the parameters just sum up. Okay, so if there are 2 spiders of different colors, and if they share, they can't share with 2 more than 1 leg. So let's say if they have 2 legs shared, then they will get how to say, the leg will be chopped and they fall apart. So they hit each other. So basically, if they're different color, but if they share 1 leg, it's fine. Okay, so in formally, so the Z spider for qubits, so it's just we have n inputs, m outputs, and m could be any natural numbers. And another color is alpha, a red spider. So they have can be actually inputs and outputs. And yeah, so that's the that's how we use the spiders to fill in the box. But except for the rules we just mentioned, like the fusion rule, right, and the leg chop rule. You may add more rules. We will mention more rules later. You may add more rules to guide their behaviors, like the copy rule. If there is one red, they can be copied by the green, green can be copied by the red, and this one they can, if they connect it to this green connect to each red, and this green also connect to each red, then they can be flipped, but keep the number of inputs and number of outputs. Okay, that's for example, that's you can add some rules to how to say to guide the behaviors. But the problem is, okay, so how do we know these rules to add it are correct, right? Does it make sense? Can we randomly add some rules? But of course you can't do that. Then how do we know that? How do we know that we add the rules correctly? So to do this, it's like in logic theory, you need to find a model for you need to find a model for your theory, right? So here the same. So you have graphs, you have diagrams, right? These spiders. But how do we know the rules you added are correct? So you need to interpret them in another system, which we already know they are reliable. So what we already know reliable is the matrices, right, or the Hilbert space formalism, right, in quantum theory. So we interpret these spiders into the matrices. So this is basically if n is equal to m, it is just the diagonal matrix. It's just diagonal matrix. If if for x is this one, but this the cat plus state is this 1 1 basically. Cat minus is 1 minus 1. So and for the other diagrams, you just compose them, right? If you have two diagrams, they composed in parallel, and then the interpretation is just the tensor product of two matrices. If they are in sequentially and then they connect sequentially, then the interpretation is just the multiplication of these two corresponding matrices. So that's the way how to interpret diagrams into matrices. If you do this, then okay, that means okay, if you have the matrix interpretation, then we can check whether the rules are good, are right. So that means okay, so that means there's no problem. You as a system, reasoning system, there's no problem there, right? No contradiction there. So this property is called sound, right? So again, so and the sound means okay, there's no problem with those rules. If you interpret the diagram into matrices, there is no contradiction. And this is proved in the first journal paper by the first journal paper of ZS calculus, which is this paper by the same author, Bob and Ross. So this is easy to check the soundness. Also, we care about the expressive power of this diagrammatic language, ZS calculus. So that means okay, can I represent any? So I can interpret each diagram into a matrix. But on the contrary, can I represent each matrix by this kind of diagram, by ZS diagram? So if yes, if the answer is yes, this property is called universal. That means okay, this language ZS calculus is universal. So it is also proved in this the same paper that the ZS calculus is universal. That means okay, you can represent any matrix in ZS diagrams. Oh, okay. The last property of this diagrammatic system is that it is the reasoning power of this graphic calculus the reasoning power is strong or not? That means, so if everything I can do in quantum theory, everything I can do is I can just use the matrices, vectors, matrices, right? But then I can have derive a lot of results, quantum computing, quantum theory results. But if I represent matrices into diagrams, can I do the same thing, but without using the matrices calculation? Can I just use the diagram calculation? Can I do that? So if you can, that means okay. The reason power of this graphic calculus is strong enough, and we call them complete. So let me briefly introduce the completeness results, because the proof of the completeness for this graphic calculus is the most difficult part. So, and historically, it took like how many, like 10 years, something like that, to prove it. So at the beginning, like Miriam proved, okay, for a part of the diagram, for a fragment of the graphic calculus, that means, okay, the angles, they are multiple of pi by 2. Then it is complete. Okay, for this part is complete. That means for this kind of matrices, they can be that's called the Clifford part. They can be the reason power is the same as the ZS. And then how about the Clifford plus T? That means the angles in the spider, they are multiple of pi by 4. And then people the French from France, the French team, they proved that, okay, in 2018, they proved that, yeah, it is for Clifford plus T also complete. Then me and another Kangfeng, we proved that, okay, so we can for any, not just like the spider angles is multiple pi by 2 or multiple pi by 4. So for any real numbers, we can show that they are complete. And so this is basically yeah, the idea, but I don't want to show much. The idea is the detail. The idea is basically borrowed from another related graphic calculus, which called ZW calculus. But then after that, people try to make it the proof. They use different proof to improve the techniques of this proof, but the result is already there. So yeah, so that's the basically the brief history of the completeness results of ZS calculus. But mostly people use people use the following one, this one, for this one, this table, this blue table. Let me explain a little bit. For the qubit ZS calculus, that means if you just use these rules, I will explain later. Sorry, I will explain later what do you mean by you use these rules. We could rewriting. I will show you what is rewriting. So if you use these rules, and so in this ZS calculus, you have two things to do. So one is, we just mentioned, you use the diagram to represent a matrix, right? And then how do you do the calculation? So we said it's composition, right? Composition, either sequential or parallel composition. But then how do you derive from one diagram to another diagram? Then you use these rules. That means you can replace for any equality here, you can replace one part with the other part. So that's the basic idea. So actually, when people found that, okay, with this A rules, is enough for the reasoning about qubits is enough. So that's nice. You don't need much. You don't need to add too much rules, right? But the problem is, okay, is that finished? Is that is that all the work about ZS calculus finished? Because we have the completeness, but no, actually not. So having completeness of ZX is not the end. It's actually the beginning of the ZX calculus. Now, which means you have a good start to apply this graphic calculus.
So can I interrupt with another question here? If
Yeah.
I go back a slide,
Back.
one slide. Yes. Okay, let's take the diagram in the very upper left corner.
Yeah.
And
Is this
just the left half of the diagram.
the S one? Okay.
Before the S, to the left of the S.
The left.
Yes, just that very upper right. I'm just wondering how to interpret that. Or is that something you're going to work toward? We have two spiders. Those are two operators.
Yeah, that's a very good question. That's a very good question.
Is that two matrices and the interaction between them? Oh, I guess we're going from one matrix operation alpha, and then after that applying beta. Is that it?
Yeah. So you want to know the so basically here you want to know how do we compose them, right? If we write them interpret them into matrices, right?
I guess, am I to understand that what you're representing there is two matrices alpha and beta, and you're composing it's
this composing
beta circle alpha. Is that what's going on there?
Actually, this that's a very good question. Actually, this composition is not a single it's not a pure sequential composition or pure parallel composition. It is a mix of both.
Okay.
Yeah. Okay. So the problem is how do we apply ZS calculus? How do we apply them? If it is not very useful, then why should we care? It's just like a math game, right? So we need to know how to apply it. But before we know how to apply it, technically, we want to know the idea, the general idea, right? The general idea is like okay, so the playing the ZX diagram is quite similar to playing with the Go game, the Go game. The Go game, so so like in this picture, there's a board with some stones, black and white. So if you want to play a Go game, if you don't care about if you don't care about any win, right? You don't want to win. You don't care about whether win or lose. So you just very easy, right? To play it very easy. Just put stones on the board. Just put stones. So the same for but if you want to win, right? If you want to win, you want to play properly, you need to think carefully. That means you need to have very good strategy, right? That's what AlphaGo did, right? So you need very good strategy. And then for ZS calculus, is very similar. If you don't want to really solve problem, just play with it. Then you just put a diagram. You just connect them, and you connect them, and you randomly use some rules. You don't care about which rule. You just randomly use it. But if you want to solve real problems in quantum computing problems, then you also need a very good strategy. That means you need each step. So each step you need to very carefully choose a rewriting rule, and then You should care about the, yeah, and then you care about the order, right? So which in this step you use this rule, and next step you use that rule, not the other way. So so strategy is also very important. That's the basic idea. It's like Go game. So below I want to show some examples. So the first example is we call quantum circuit optimization. That means you want to give a quantum circuit, you want to make it how to say, make it as simple as possible, but don't want to change it. And to do this using ZS calculus, so you need to first you need to translate a quantum circuit into a ZS diagram. This is very easy because quantum circuits is composed, right? Any quantum circuit is composed of the quantum gates. So you just need to translate the quantum gates, right? The quantum gates into quantum circuits, into ZS diagrams. So here is the very typical one. Here are some very typical quantum gates. So the Harman gates, you just translate in Harman. So by the way, I didn't mention the Harman is not a spider, but it can be composed with some spiders. But for convention, to make it convenient, so we usually use a Harman node to represent it. Okay, so you just change it to Harman node, and the S gate is just this green spider with one input, one output, and the angle is pi/2. The S dagger, the inverse of the S gate, is the minus pi/2. And then similarly for the T gate is just the pi/4, and the T dagger gate is the minus pi/4. So the poly Z gate is just the green pi with one input, one output. The NOT gate X is just a red pi with one input, one output. And this control Z is just two green with Harman in the middle connected. So this one I didn't draw it properly, but this C0 gate, which is in ZX, which is exactly, I mean the semantic. When I say the translation, keep the semantic. If you kept the symmetrics, the exact the C0 gate. So that's the control part. That's the target part. So you have a very easy direct translation from the quantum gates to ZS diagram. That's one. That's why a typical application with ZS calculus is for quantum circuit simplification. So now I want to give an example.
Before you do that, Neil, do you want to ask a question out loud, or should I read it for you?
Yeah. Please.
Okay, let me read it. How do you determine that the S gate is to be translated to a green spider with pi/2?
Okay.
Or generally, why are those specific translations?
Yeah, that's a good question. Yeah, because as I just mentioned, for the translation is you want to keep the semantics because each quantum gate, they corresponding to a matrix, right?
Right.
And also each ZS diagram, they corresponding to a matrix. So they should if they corresponding to the same matrix, then you can use it to represent it. You can translate in that way. That means you preserve the semantics. That's the way.
Okay, I mean, I guess I have a follow-up question, and everybody can chime in if this is obvious to everybody else. Why is Z a green gate and X a red gate?
Why use the color red and green?
I'm not talking about the colors, red and green. I understand
okay, the Z spider and X spider.
Yes. Why is Z a green? What is it about Z that makes it a green spider as opposed to X being a red spider?
Yeah. So Okay, let's take the example, the poly Z, right?
Right.
The poly Z, or the matrix of the poly Z is a 2x2 matrix, which is one under the diagonal is a diagonal 2x2 matrix, and the diagonal elements is 1 and -1, right?
Right.
Yeah. Okay. Then let's go. So that's the poly that quantum gate, and the green pie with one input, one output. If we look at the definition, so it's here. So if we look at the definition, then so is here. Then N and M now is one. So sorry, here the diagram, sometimes I draw from top to bottom. Sometimes for the quantum circuit, I draw from left to right. But anyway, so now the N and M is 1. The both are 1, right? Yeah, is 1. So basically, but each, as I said, each dimension is 2. So it's a 2x2 matrix. So this is also a diagonal. And the alpha now is pi. So EI pi is -1.
Okay.
Yeah, so you got 1 -1 here. Then all the other elements are 0.
Oh. All other elements are 0. That.
Yeah. Sorry, I didn't mention that. All the elements are 0. So
Okay. All right.
these two are 1 and e to I alpha. Yeah.
Okay.
Yeah. So
and not so for the X gate.
yeah. So yeah, you just calculate it. Yeah.
Okay. All right. Thank you.
Yeah. That's a very good question. Yeah. So yeah. So you keep the semantics and you got a relatively simple diagram. And then, okay, so that's a translation. That didn't show the power. Let me show the power. So I give example. So this the CCZ. Here is a circuit, which is composed of 4 CCZ, 4 CCZ gates, right? But they are on different wires. So there are this circuit. So we will see that each CCZ, if you turn them into quantum gates, you will have normal. Typically, if you use like the Clifford-Plasty quantum gates, so you will have some T gates, so the number of T gates is called T count. So each ticket, so it's ticket is expensive and very hard to implement on a quantum computer, much harder than the Clifford quantum gates. So people want to reduce the number of tickets, as small as possible. So the problem is, okay, if we realize this quantum circuit in the Clifford-Plasty circuits, how can we get rid of most of the T gates? So typically each CCZ gate, as here, so they can be implemented. Because the ZX diagram and the quantum gates, the quantum circuit is very close, so I just draw them in ZX form. So you can see that if you write down them in this is the C naught and this is the S dagger, this is the S gate. So if you draw them in the ZX diagram for this quantum circuit, use Clifford-Plasty, you will find that okay, for each CCZ gate, if you will have 1, 2, 3, 4, 5, 6, 7. You have 7 T gates, and minus pi by 4 and pi by 4, they are both T gates, counted as T gates. So you have 7 T gates, and in this quantum circuit, you have 4 CCZ gates, right? So that's 4 times 7. You have 28 T gates. That means the T count of this circuit is 28. That's a lot. So we want to try to use ZX to reduce the number of T gates. to reduce the T count. So by the way, if you look at just look at the gates, quantum gates. If you realize this circuit in 34 plus T gates, so then if you don't use the then usually how do you do that, right? How do you do the simplification? You can think about it. It's not the trivial thing, right? So okay, so how could ZX help here? So I just want to so the idea is, okay, I want to, for each, there are 4 CCZ. So for each one, I want to how to say, simplify for each CCZ first, and then I want to put them together and let's to simplify again. That's the idea. Okay, how do I simplify each CCZ gate? Let me show you I will start from very simple, relatively simple ZS diagram. So if I have a C naught, I have 2 C naughts and one one alpha gate. That's the rotation Z rotation gate, right? So if I have this rotation gate alpha, the angle is alpha, and have 2 C naughts, can I make this relatively how to say, simple? Then I can easily use them to simplify the big circuits. So here, so I first do some rewriting. So what I mean is, okay, so what I mean rewriting means, okay, I just I look at the part of the diagram and to see what I can do. So here, because here these are two green. So as we said, they can fuse if they are the same color. So then I fuse them together, right? They use the fusion loop. So I fuse them together, but I can also do the opposite way. I can unfuse them. I call it fusion is a fusion loop. I can unfuse them, right? I can unfuse them in this way. That I can unfuse them in this way. It doesn't matter. Just unfuse them, and then I can move them. I can move freely. So to this alpha, I drag the alpha to this place. I move this a lot. So I didn't mention rule is any topology, any connections matters. So if you don't change the connection, it's fine. So it won't change anything. So I just drag them. I drag the alpha here, and for this alpha, I unfuse it again. I unfuse it again because alpha and this. Sorry, I didn't say that if this phase free, if there's no any phase, that means there's this is the phase 0. So I can unfuse it because when I fuse them, it's just a plus, right? So I can unfuse it again. I drag it. So why do this? Because for this part is what we call the bialgebra loop. That means, okay, I have 2 green and 2 red, and each green connect to each red. That's then we can swap the order. So green on top, at the beginning green on top and red at bottom, and now I can change, but keep the inputs number, keep inputs and outputs. So this is the what we call the bialgebra loop. So that means, okay, I replace this part. I replace this part with this part. That's the other side of the bialgebra loop. So when I do this replacement, this is called rewriting. Okay, so okay, the other parts keep unchanged. I just replace this with this. Okay, that's how I use a loop to do rewriting. And then okay, I just make it properly, make it more beautiful. So I get this. It doesn't matter where you put it. So I put it horizontally here. Okay, then you got this. That means, okay, use this kind of rules rewriting. I start from this diagram, I get this diagram. Because for this diagram, I just need one red spider here. Okay, and then so how about if I have a one signal and one rotation, and similarly I can do some rewriting. then I will get, okay, I can pass, this C naught can pass through this alpha, then I will get this. I will get C naught from left to right, to this right. But you can't just pass, because these are different colors, you just can't go through. So you will have more extra connection. That means you will get this thing, similarly, if you this C naught is on the right, you will also you can also commute this C naught to the left, but you will have this gadget as well. But if you have this gadget and you connect, you want to commute with this C naught, then you will get this more lax gadget with this C naught commuted to the right. So basically, when I have C naught and the rotations of all these kind of gadgets and C naughts, I can do some kind of commutation. So why do I do this? So let's give them proper name, like this kind of thing. This kind of thing. I have 3 nodes, like a few green nodes. A few green nodes connect to a single red nodes, and with the angle here also connected. So this kind of thing we call them phase gadget, and if the 2 phase gadgets, they operate each green, they are on the same wire, and then they are the same shape. Just the any difference is, if the any difference of 2 phase gadgets are the angles, then they can fuse as a green spider. They can fuse as well. They can fuse to be a new phase gadget, and the shape is the same, just the angles they also summed up. Okay, that's how do you fuse to phase gadget. It's very simple.
John, do
Okay.
you want to ask your question from the previous slide?
Okay, yes, please. This one?
Before that.
This one?
John, do you want to unmute yourself? Or I can ask?
Yeah.
Okay, I'll take the initiative. John says the very last rightmost circuits are different from second row to third row.
Yeah, this one, right?
Uh,
Do you mean this and this?
rightmost, the very last rightmost circuits
Rightmost.
are different from the second row to the third
Second row, okay.
So this is, yeah.
Yeah. This one.
And are they different?
This one, and which one? Sorry, I didn't hear the first.
John, do you want to help clarify your question?
This one and which one?
John, we couldn't hear.
Yeah. I can't hear.
Titus says Mike is not giving any input. So yeah, I guess the question is, are those 2 circuits, the last circuits of the second row, and that
Last set of the second row, oh, that's this
right,
one.
and that of the third row.
The third,
Right.
which one?
Are
The
they
first.
different?
The first.
Or the last, I guess.
The last, okay, this. The last of the third row and the last of the second row.
Yeah.
Yeah, they are different, because you can see clearly they are up to C naught. Yeah.
Okay, so they are not the same because of the extra C naught.
Yeah, because you have a C naught. C naught is a unitary gate, it's not the identity.
Okay. All right.
Okay, so if So now I will start from a CCZ gate. CCZ gate, when translated into quantum circuits, when implemented into quantum circuits and translated to ZX diagram, it looks like this. It looks like this. And now I want to use ZX to simplify this whole thing. So how do I simplify it? Is okay. So I first move this. Sorry, this is a pi. This is a ticket. I move from here because these are green. These are all green. So I can fuse and unfuse and fuse and unfuse, fuse and unfuse. Then that means I can just move them to the left. Similarly for this pipe, for this the second left ticket, I can, because these two nodes are red, are green, the same color, so I can also fuse and unfuse and fuse and unfuse and move to the left. So I can move them to the left to make it clear. And then, okay, then what's left? What's left is okay, is all this kind of thing. You can see is a C naught, and is a T gate, is a alpha gate, rotation gate. C naught rotating gate, C naught rotation gate, and C naught rotating gate, and two C naught and with notation inside. And this is what we just considered. The C naught with the rotation, C naught with the rotation on the left or right, and two C naught in the middle. So we can replace this this thing with this gadget, and this thing with this gadget and the C naught, this thing with this C naught and this gadget. And then if we do that, we will have this. We will get this gadget, C naught, gadget, C naught, C naught, C naught, gadget, C naught, and this one I didn't do anything. So and then we have two C naught here because of the previous process. And then what we will do is that we can move, because here you can see this color are the same. This color are red, and this they're on different wires, so they can just commute with each other. Just commute. So I will commute. So finally I will commute and commute, then I will get this. So here then what should I do is, okay, I didn't show the half floor, but anyway, that means we all know that in quantum circuit, we all know that if we have two C naught, they are on the same wire, right? On the same wire, the controls are on the same wire, the target on the same wire. So if we have these two C naught next to each other, then they just cancel out, right? They just cancel. Similar, these two C naught, they just cancel out. These two C naught just cancel out. Then we have this. Okay, then we have we will have this all these C naughts cancel out. So that means all these C naughts, 1, 2, 3, 4. These 4 C naughts cancel out, then there's no red anymore, right? No red anymore. So that's why this all green on the bottom line. So that means, okay, I can move this pi by 4 to the left. So I get this. So what is left is, okay, I have get 3 rotations, and 1, 2, 3, 4. We have 4 gadgets. Okay, so that means, okay, for each CCZ, I can write it in this diagram as this. That's what I just did. And then why do I do this? Because now I need to put this is and why do this? This is a more compact form of CCZ, and then I put them together. I put them together. I didn't show here because I didn't show the process again. But but because of the if you consider the positions, I put them for each one you replace with this, but you consider the positions, right? The positions of these nodes, and then you will find out that okay, so because you can see for on each while, you can see on each while they're all green, on each while they're all green, each while all green, so they can commute, so they can commute with each other. So that means if you so that means, okay, if on the same wire you have pi 2 pi by 4, then they will fuse together, get pi by 2, right? So that's why here we got pi by 2. If we have followed, then you just got pi. And we also said for this phase gadget, if two phase gadgets, they are on the same wires, then they just they can also fuse and with the angles they add together. So then if we do this kind of thing, as I just mentioned, fuse the phase gadget and fuse the single rotations, and you will get this diagram. And then you count. This diagram is because I just do rewriting keep the semantics. So the idea and change the semantics to the quantum circuit. But for now, as we said from the beginning, you can see we have 4 CCZ, and each CCZ has T count 7. So 4 times 7 is 28. But now, if you after we do this cancellation fusion, so let's count how many pi by 4 now. 1, 2, 3, 4, 5, 6, 7, 8. So now the T count is 8. So it's reduced from 28 to 8. So by this technique, using ZX rewriting, we already reduced the T count from 28 to 8. Okay, that's a kind of magic. We didn't do any matrix calculation. Okay, but is that the end? Actually, no. We can make it even less, but of course, it wouldn't be so significantly. But what we can do is, I don't want to I just give the idea. So we find out some ZX identities, which is composed of these phase gadget and the single notations. If you put this one, that means for each wire you have pi by 4. For each 2 wires you have you have pi minus pi by 4. For each 3 wires you have pi by 4, and finally for the 4 wires you have a single phase gadget have minus pi by 4. So if you put this all phase gadget together, you will get actually cancel out. They will be identity. So that means if you apply this all this left diagram on a quantum circuit, that means you don't change anything, right? You don't change anything. So here I didn't put the angles. More complicated. If there are 5 wires, not 4 wires. If 5 wires, you have this. This is also symmetric. That's mean each 2 wires, each 1 wires, each 3 wires, each 4 wires, each 5 wires. They have some phase gadget. And then you put them together, you will get identity. For this identity, we call them. We have a name called spider nest identity. So identity also means if you put the phase gadget on the quantum circuit, it won't change anything because they are essentially identity. So, so how could this help for T count reduction? So that means if you have more than half of, as we know, so for the 4 CCZ quantum circuit, so we simplify it to phase gadget, right? We have some phase gadget to represent it. But if for these identities, we also have a lot of phase gadget. So they could cancel out, right? To become non-tickets, right? So if you have more than half of the phase gadgets, so what I mean is, if given a quantum circuit, if already you turn them into phase gadgets, if the number of phase gadget is they have the number of the alpha the angles are tickets, right? So if they half of it, if half of it, the ticket phase gadget, they are more than half of the let's say 4 wires. The spy nest identity we have like 50, something like that. So if you have more than half, that means if you have 8, we have 14. So if you have 8, at least 8 already there, then that means they can cancel out. Then you will reduce the count. That's the basic idea. So similarly for the 5 wires identity. So if we apply those things to them, if we apply these 4 wires and this 5 wires identity to this final phase gadget, then you will cancel out something. So for the first 4 wires, we apply the 4 wire identity. For the whole 5 wires, we also apply the 5 wire identity, because identities won't change anything. But phase gadget will cancel out with each other, and you will reduce T count. Then you will from the 8 T count 8 to 1 more T count 7. I don't want to show the detail here, but that's the idea. So use this idea. We looked at this all these benchmark circuits, and we found out that it works very well use this method. Similar for this more benchmark circuit. So we use those identities. Works very well. Okay, quickly I will show some more applications. So I want to say that not only for quantum circuit simplification, and you can also represent like quantum cryptography protocols like BB84 and ACT91, and they are essentially that the structure, the pattern there, why it works, the protocol works because of this property of the spiders. And also we can use for any matrix of a size 2 to the m times 2 to the n, you can also represent them by ZS diagrams, and you can do if you look at the paper, you can do Gaussian elimination using ZS diagram, not the matrix. And also you can do for a matrix, because each diagram, ZS diagram represents a matrix. But if each matrix is a function, is a real function, then you can do differentiation, right? So you can do matrix differentiation and integration. So you can also do them by ZS diagrams. Here, like if you got the diagram here, then after differentiation you get this diagram. And also you can do some you can sum up things like Hamiltonians. Usually people write Hamiltonians in terms of like polys, right? Poly operators, sum of poly operators. Then you can also represent them by these diagrams. Here we show example for the proof of linearity of Schrodinger equation. And finally, I want to mention that's what we did relatively recently. That means, okay, hey, there is something like in spin networks, which spin networks is like used a lot, like in quantum gravity or in quantum chemistry, used a lot. The key part of the spin network thing is the irreducible representations of the SU2 group. So basically this is a people call symmetrizer, right? The representation basically symmetrizer. And with the symmetrizer, if you use it as a linear map, is this. So it looks a little bit complicated. Use the how to say, the permutation group. But in this paper, we find a very simple way to represent the diagram in ZX. But in this paper, we generalize the ZX, the Z spider to as I showed at the beginning, they can have different types. Each leg have different types. And then in this way, you can represent the symmetry in this simple way. And then you can do a lot of simplification for spin networks. So that's the thing. So at the end, so if you want to try to use the X, you can do what kind of thing you can do. As I mentioned, quantum circuit optimization and also quantum error correction. Like I think like Peter showed also they have a paper to use the X to do this kind of quantum error correction, and also quantum machine learning. You can analyze the Baron-Prater phenomena. Also in quantum chemistry, you can do Hamiltonian simulation and angular momentum coupling problem to this kind of thing. And finally, as I just mentioned, the spin networks. Okay, that's the application of the ZX and something you can try. Okay, thank you, everyone.
Oh boy, thank you. This makes me want to read the original book. 1,000 pages, something like that. Big one, right?
That's the book you mean?
Yeah, yeah.
Yeah, that's like 900 pages.
900 pages.
Yeah, there's a lot of things there, but there's a lot of things which is beyond the book here.
Of course, of course, of course. We have about, I don't know, 15 minutes for questions. It says, John says, where could we have access to this presentation? Slides. If you want access to the slides, Harny, I assume that you can make the slides available?
Sure. Yeah.
Okay, all right. Why don't you shoot me a message in the meetup group chat or the meetup group messaging, and I will email a copy to you. Anybody who would like a copy of the slides. All right, do we have questions? We have about 15, 12 minutes, 30, 13 minutes for questions.
So thanks for this presentation, Harry. So this ZX calculus, it defines processes, and you had a mechanism for mapping them onto qubits. Is there also a way to map them onto qubits, or?
Yeah, that's a good question. For qubits or any, that's for not because I said qubits is easy to explain, but what we have done is we actually did for like a job is like like what we did recently here. We can represent any, like here we can represent any matrix of any size, m times n, any size, because for qubits the corresponding matrix is like power of 2, right? 2 to m times 2 to n, right?
Oh, very cool.
Yeah, so here you can do any dimension, m times n. So actually you can represent any like, or in other way you can say that you can represent any tensor, because a tensor is a linear map from finite dimension to finite dimension.
Sounds like it'll be useful if anybody starts building qubits or bigger ones.
Yeah.
Also, your equivalent
Mom, excuse me.
equivalency.
I'm getting called by a family member. I'll be back in 2 minutes. Okay, Ron,
No
you're
problem. Thanks.
Sunil has a question in the chat.
Yeah. So those equivalency rules, I assume that they're proven via matrix math or linear algebra proofs on them.
Sorry, can what's the
So
question?
you have a set of equivalency rules that show how one graph is the same as another graph.
Yeah, so the rewriting rules, you mean?
Yeah. So those are like this set. These are proven via with actually using matrices. in linear algebra?
Yeah. So when you want to prove the rule is correct, that we call soundness, then you need to check by matrix, or usually we don't directly check by matrix. We check by because they are linear maps, so you just need to consider the basis. So we check by the standard basis.
Okay. All right, Sunil, did you want to come on the mic?
Yeah, I can do that. Is there a
Yeah.
list of recommended papers / books? Because there's an awful lot of those out there, and I'm interested in like finding out which ones are the ones that are worth reading.
Yeah. You mean some like introduction?
Yeah, introduction, and then
Yeah.
like a guided tour through this stuff. So to get up to
Yeah,
speed.
so that's a very good question. So I think first, so all the resources about the ZX calculus papers or books, they are on a website called a website just zxcalculus.com. I think they have introduction papers, and yeah, everything is there.
All right, great, thank you.
Okay.
So George, I heard you on the microphone earlier. Do you want to come on and ask your questions?
Yeah, sure. Thank you for a very interesting talk. And I understand some of what you were saying in terms of tensor algebra, and that some of these rewrite rules are simplifications where things associate or commute. What I'm wondering, as a language, does ZX calculus, is that a context-free language, context-sensitive, or whatever?
Sorry, I don't know what that mean. It is context free.
Well, yeah, that's kind of a computer science question. Is what is the scope of the rewrite rules?
What's the goal?
The scope. To what extent can you rewrite an expression? Well, thinking of the graph as an expression of a grammar, your rewrite rules. I guess my question is, how powerful are the rewrite rules?
Yeah, that's a very good question. So, in principle, the power of the rewrite rules is the same as the the matrices calculations. If you restrict your calculation to just how to say multiplication and the tensor product.
Okay, thank you.
But I want but actually as I just mentioned, we can do differentiation, we can do sum, we can also do sum, but we can do sum of two diagrams just use this diagram, use CX.
And George, you were asking about Turing complete. Does that?
Yeah, because somewhere you had mentioned like that the gadgets, the spiders formed a complete basis, and
a standard basis, yeah, people.
A standard basis, in the sense that in terms of gates, the Pauli gates form a complete basis, and this kind of corresponds to the Turing completeness of quantum computing. So I guess my question is, you hinted at that there was a difficult paper which showed completeness of the ZX formalism.
Yeah, that's the completeness paper, yes. But
okay, thank you.
Yeah.
That's what I meant by Turing completeness, in the sense that it's, I guess the other word would be universal set. Yeah.
So I might Yeah, George.
So yeah, anyway, thank you. This is really a lot for me to think about. So I look forward to looking at the further references.
Mhm. Yeah,
I
so
guess-
everything, yeah, as I said, everything is on the zxcalculus.com website.
There are a million papers listed there.
Yeah.
I'm looking it over. I'm always looking for ways of explaining simple quantum algorithms, simple quantum computing algorithms to people who aren't familiar with quantum computing. Is there an example of the use of ZX diagrams
For quantum algorithm.
to explain, to make very intuitive the way any of these algorithms work?
Yeah, that's a that's a very good question. There is some I think in the, as I mentioned in the third book, they have some examples using ZX for quantum algorithms, and also I want to mention that recently we have I think it's in, I just mentioned, I think it's in this paper here. This paper we no, sorry, not this paper. It is recently in another paper we showed very simple way to represent the quantum Fourier transformation.
Okay, all
So
right.
this paper we showed in this paper we showed how to represent the quantum Fourier transformation in this formalism.
I'll have to take a look at that. That's good. Any other questions before we conclude? We have about 3 minutes left, and I have only half a minute of concluding remarks. Oh, here we go. Did ZX calculus play any role in how Quantinuum, in collaboration with Microsoft, achieved their latest breakthrough in error correction? Harny, did you hear the question?
Oh no, sorry, I didn't. Yeah.
The question is from Carrie. Did ZX calculus play any role in how Quantinuum, in collaboration with Microsoft, achieved their latest breakthrough in error correction?
I'm not involved in this.
I'm going to voice an opinion about that, and it was, in my opinion, old news. I didn't get what they were bringing to the table all of a sudden. They used 32 qubits to build 4 logical qubits, and they're real excited about this, but they're somehow have gotten higher resilience. But these are techniques that I've seen going on for the last year or so. So I wasn't really sure what it is that they were so proud of. But you would certainly want to have any circuits involved in the logical compression to be as efficient as possible. So if they didn't use the X calculus, they probably should use some other optimization routines.
Harry says they increased the number of qubits and their results were 800 times more successful than any other test to date.
Well, that's according to everything I've read anyway. But it sounded like
that's what they claim.
Well, hey, that's what we got to go by, at least until we know otherwise. I guess it's curious to me just because Microsoft, it sounded like they were testing their virtualization system for qubits. So I wasn't sure if maybe in an underlying sense, just the understanding that was created, through this process maybe contributed or not. But it doesn't sound like it had like a direct application in that. So I appreciate that.
The whole system looks very powerful, at least in terms of visualization of processes. And I'm always excited to learn about new visualizations. It just seems as if they just the world goes forward when we can visualize things and use those visualizations to increase our understanding and discover new things. Harny, I want to thank you. This has been an excellent presentation, and it's, I don't know, speaking for myself, it started me on a road to learn more about the ZX calculus. With that, I guess it's time to wrap up. Don't forget, we have a meeting on July 11th, Chicago, Illinois, and beyond quantum computing meetup. On July 11th, we'll be meeting and talking about the Q# programming language. We hope to see everyone there.
And also, if anybody has any speakers they'd like us to pursue or topics they'd like us to pursue, please contact us through the meetup site and we'll see what we can do.
Thanks, so.
Always looking for good speakers.
Okay, thank you.
Thank you.
Thanks again, Harry.